where y equals some function, right? And we can satisfy that with saying if it's if the function is k times y, then we can take the derivative of that and it'll just be k times that function, okay? But that's true if and only if you could see down here, we have this y equals, or f of x equals some constant times k raised to the x. Okay, so if you remember last class period, we looked at doing derivatives where we had e to the x, right? That derivative is itself. And so this kind of is a little bit of a continuation on that. Okay, and so there's some discussion in the textbook. This won't be something that's on the test, but you will see it in the homework, right? About the uninhibited population growth. I believe that's on page 219 in your textbook. But essentially, it says we have this equation here that I've written out here, the dp over dt equal to the kp. And so when we take the derivative of that, right? So the derivative of p in relation to t is just k to the pt. Okay? And this is really just the basic model for uninhibited population. And so what does that mean? Uninhibited really just means, in terms of what we're looking at, it's an unrestrained growth. Okay, so whether we're talking about population or bacteria that might be growing, or money that we're investing, whatever that might be, we're not inhibited, right? So, but the problem is we can't grow a population exponentially forever and ever. We can't. There has to be some sort of limiting growth to that, and so that then our limited growth is a logistics equation, okay? And so that's going to be our P of T is equal to this capital L, where that L is our limiting factor, divided by 1 plus C e raised to the negative LKT. Okay, so this is not something that you guys need to memorize this formula or anything like that. There will be a homework problem or two for you to get a little bit of practice with that. This is one of those things, if you were to see this again on an exam, you would not need to memorize this formula. This would be provided to you, okay? And so, but basically it is one model for population growth in which there are factors that prevent the population from exceeding some limiting value. That's, again, like I said, that capital L. Some things that could be limiting factors on population might be food or natural resources or living space, things like that. Okay. And so that's when we would take into effect that. And we'll look at an example in a little bit about turtle population and how we can determine the limiting population of that based on the this growth limit. Okay. All right, so if you're following along in your textbook, page 226 is where the problems begin. And so for this first set of problems, we do have we're asked to find G if our G prime is 6 times some function, right? So this is like problem numbers 1 and 2 in the textbook. And so essentially, we are given that theorem 9 here tells me that I can just use this here. So if my derivative, right, is this k times my function, then, and my function is c times e raised to the k x, then in this case, we could say then that my function g of x is simply c e to the kx, where if we look right here, this right here tells me that my k is equal to 6. So we could say c times e raised to the 6x. And so that's all there is to that. And you'll probably see one or so of those in your homework for practice as well. Okay? Question. Okay, so the next problem asks us to find the derivative or find the function that satisfies what we see here. And so in this case, if we let our initial population at time 0 or t equal to 0 be p naught, p naught in the terms of this, so p naught is just p sub 0. It's red p naught, but really that is just your initial value. So in this case, because we have a p, we're saying p is a population. But in the financial thing, it could be p could be your principal or something to that effect. Okay. So don't get too tied to the p. It could be other letters as well. Okay. So for this one, though, we want to determine this. So my function or my p, my population, is this ce to the negative 3t, right? Because this right here tells me that my k is negative 3. So that leads me to c times e to the negative 3t, since we're talking t's here instead of x's. Now, when we have a negative there, that actually tells us that we have decay and not growth. Okay. And so we could rewrite our p equals c times e to the negative 3t. We could write that in terms of a function where it's p of t, where we're looking at it in respect to time, and the remainder of the equation stays as is. Okay. So, and that would be true for some constant c, which is what that c is represented in our equation. So ultimately, p naught, or our initial value, right? So if I wanted to look at p at time 0, that is going to be my p naught. So it'll be my function evaluated at time 0. So c times e to the negative 3 times 0, which gives me c times e to the 0, but e raised to the 0 is 1, so that would give me c. So my p naught is equal to c, and thus we can represent it as what we have showed here. Okay, so that's a lot more in detail than what you really need to know for your homework, but that is the backing behind why each of those values transpire how they do. Okay, questions? All right, so for this next problem here, it is an application, right? As I mentioned, this section is pretty application heavy. So for problem number 18 on page 227, actually it's problem number 8, not 18. On page 227, we're looking at a franchise, right? So This franchise is selling franchises for a pizza shop throughout the country. The marketing manager establishes that the number of franchises, capital N, will increase at a rate of 10% a year. And so we need to A, find the function that satisfies this equation, assuming that the number of franchises at time equals 0 is 50, right? So when we, in the initial, we start this out, we're going to have 50 franchises. And then we want to know how many franchises there are after 20 years, and then we want to know what the rate of change is after 20 years. So remember, if we want to just know the number of franchises, then we're going to just use our initial formula, plugging in 20 for time t. When we want to do rate of change, remember that is the derivative. So we'll take the derivative and then plug in 20 to determine what our rate of change is at 20 years. Okay. So for this one, we were given that dn of dt is equal to 0.10 times n. Okay. So we want to find the function. So in part A, we're finding the function. We first have to assume that t equals 0 is 50, right? That was something that we were given. So by substituting n naught equals 50 and k equals 0.10, we would get n of t is equal to n naught, that's our initial value, times e raised to the kt. So we substitute in the two things that we do know about this, and we get that n of t is equal to 50 times e to the 0.1 t. Okay. So in part B, when it asks us to determine the number of franchises that there will be in 20 years, we really just have to take our formula and substitute in 20 years from now. And so that is 50 times e raised to the 0.1 times 20. And that will simplify to about 369 franchises. Okay, so we have 50 franchises today. We're going to grow at this rate of about 10 per year. So in 20 years, we should have about 369 franchises available. Okay, question. So the next part is it wants to know what the rate of change is in the number of franchises in the next 20 years. So we take the derivative, which our theorem 9 tells us is k times n of t, right? And so we do know that we're looking for the derivative in 20 years. We also know that our k is a value of 0.1, and our n of t, or n of 20 years, we calculated up above, right? And so that is going to give me 369 times 0.1. And so that is 36.9 franchises. And so that tells me that the rate of change in the number of franchises in 20 years will be about 36.9 franchises per year. So we'll be growing that in year 20, we'll be growing about 37 franchises that year. Okay. Question. Okay, so we do have one more example for this section. And so this is on the limited population growth, right? I gave that formula on the first slide. But essentially for this problem, it's saying we have this limited growth population of the tortoise population. And so in a square mile of the Mojave Desert, after T years, can be approximated by this logistics equation. And so we're given this equation here, okay? We want to find the tortoise population after 0, 5, 15, and 25 years. Then we want to determine the rate of change for the population. We'll want to find the formula for it, which is just taking the derivative. And then we'll want to substitute in year 0, 5, 15, 25 to see what those are. And then lastly, we'll want to see if we can determine what limiting value for the population of the tortoises is in that square mile of the Mojave Desert. Okay. So for the first one, let's go ahead. We have it here to the left. This is our P of T. We want to find the population. So part A, we want to find the population at time 0, at time 5, time 15, and time 25. So this is, just plug it straight into our formula that we were provided with. So that's 3,000 divided by 20 plus 130 e to the negative 0.214 times 0. Okay. So this is going to give me about 3,000 divided by 20 plus 130. So that's approximately 20. So the population of tortoises after time 0 is going to be approximately 20. So what that's saying is our initial value we're starting out with in this population is, or in this square mile, is 20 tortoises. Okay. So now we want to calculate how many tortoises are there after 5 years. So we do the same exact thing, except now instead of substituting in 0, we can substitute in the value of 5. Okay, so instead of 0, we're putting in a 5 here. So it's still 3,000 divided by 20 plus 130 times e raised to the negative 2.14 times 5 this time. And that's going to give us approximately 46 tortoises after 5 years. Okay. We do it again for 15 years. Okay, so after 15 years, that's going to give us approximately 119 tortoises. Then after 20 years, or actually it's 25 years, we're going to have approximately 146 tortoises. And we could keep going on and on and on. And eventually we can see what's how the population continues to grow. But we're probably actually will end up seeing that we're going to reach a peak, right? And so before we explore any further with that, let's go ahead and move on to section B, or question B, which says find the rate of change in the population. And so that is the derivative, right? And so for this one, when we're looking at the derivative, we have, so part B, if we let the numerator of the function be our f of x, right? So f of x equals 3,000, and my g of x is equal to my denominator, which is the 20 plus 130 e to the negative 0.214t. Okay, take the derivative. So my f prime is going to be 0, right? The derivative of a constant is 0. And the derivative of my g function is going to give me 130 times this negative 0.214 times, then the rest of it is the same, the e to the negative 0.214t. Okay? So looking at that, I could do p prime of t is equal to, that is my g, 20 plus 130 e to the negative 0.214t. It's my g times my f prime minus my f times g prime, which is 130 times negative, let me, that negative 0.214 times e to the negative 0.214t. All of that divided by my g, which is 20 plus 130 e to the negative 0.214t squared. Okay? So when we simplify this, it actually ends up being 83,460 e to the negative 0.214t divided by our denominator. We can just leave as the 20 plus 130 e to the negative 0.214t squared. Okay? So now that we have that, all we need to do for the third, for the part C, is we want to use that formula, right, to evaluate that rate of change at 0, 5, 15, and 25. So P prime at 0 is equal to this 83,460 e to the negative 0.214 times 0 divided by 20 plus 130 e to the negative 0.214 times 0 squared. Okay? And so that will simplify to 3.71. So that tells me that the tortoise population is changing at about 3.7 tortoises a year at that time 0. Okay? And I'm not going to rewrite all of this with each of these years, but I will highlight here this and this value is what changes from the derivative evaluated at 0 versus the derivative that's evaluated at 5 years versus the derivative evaluated at 15 years and the derivative evaluated at 25. So for each of these then, we end up with a slightly different number. So we have 6.86. So you can see we're going from 3.71 a year, but 5 years later, now we're growing at a rate of 6.86, right? So we're going, if you were to plot this, right? If I have 5 years, 10 years, 15 years, 20 years, 25 years, right? And I'm plotting the growth or whatever. I'm at 0, I was somewhere here around 3.7. At 5, I'm coming up here. At 15 years, I'm at 5.83. So I'm actually coming back down a little bit, right? So you would see something like this. So we get up there, we hit this peak, and now we're coming back down. So that tells me that we have this limiting factor, right? And when our derivative is evaluated at 25 years, we're actually at 0.93. So we're actually almost, we're really slowing down after 25 years, the population isn't growing very much anymore, right? And so we could talk about this limiting factor, and what helps us to see this limiting factor or what that value is, right? Is if we come back up here to what I did in the purple and we're looking at that, if I put in that I'm going to do, 50 years from now, what value does that get? What if I go 100 years from now or 1,000 years from now, right? So we get way, way out there. And you would think that this number would get extremely large, but you'll find that it actually becomes limited at about 150. So I would encourage y'all to just try some other numbers, right? You'll get closer and closer to 150, but you're not really going to get over 150. And so that tells me that I have a limiting value on the population of the tortoises in this 1 square mile, meaning that we probably won't ever get more than 150 tortoises in that area. Okay, question. All right, so chapter 2.4 is very short. It shouldn't take too much time for you all. I mean, there's a few problems for you to work their application, but concept wise, it's really we don't really have a whole lot of new. The one thing I do want to point out to you all is, let me see what that page number is. There will be one problem on your homework that a lot of students often get stumped on, and it's about exponential model using regression. Okay, so the one thing I will tell you, because we use the textbook, e-textbook, and so I'm sure a lot of you probably don't actually read the textbook, which is 100% okay. But I will tell you, when you get to that problem and you're a little bit stumped by it, go ahead and go to your e-textbook and look at page 221. There's a technology connection section, and that tells you and shows you how to use your graphing calculator to get through this problem, right? So essentially, when you pull up your graphing calculator, there is an exponential regression option, and you'll choose that and then plug in the information from your problem. And when you hit enter, it will tell you what your A and B values are, and that's what you will be looking for for that problem in your homework. Okay. Any questions about the application section before we move on to section 2.5?
Professor, could you go back to the previous question? I didn't get the last part. What is the limiting value?
The limiting value, the 150. Sorry. I wrote it up here, sorry.
Okay, that's where I missed it. Okay. Could you explain one more time where you got that number from?
Yeah, so I'm going to just write here a D. The limiting value is, so if we took and decided to, for this part right here, right? Instead of 25 years, what if I looked at 50? So if I plug 50 in here for this, and I actually forgot to change that to a 25, so we'll do that real quick. If I change that to a 50, I get a little bit closer to 150. If I changed it to 100, I get a little bit closer to 150. If I change it to 1,000, I'm really close to 150. I can't even distinguish really. And so I could put it as 1,000,000 and I still don't get any closer to 150 than what my calculator shows. So that tells me that my population limits or caps out at 150.
Thank you.
Yeah. Any other questions? All right, so let's go ahead and move on. So each of these three sections that we have tonight, like this one, I have like 6 slides. I think the next one only has 4 or so slides. So we'll probably try and push through all of this, take our break, and then come back and do the exam review. If unless unless this section tends to take a little more, if y'all have questions, definitely feel free to ask. But if not, that is the plan for right now. All right, so now this section 2.5, in this section, we will look at applications of exponential decay. So in the previous example or section, we were looking at exponential growth, right? So that was where our K was positive. Now, when we look at decay, and I did briefly mention it when I was talking in the previous section, but if we are looking at decay, then we would look at something along the lines of our derivative with respect to time being equal to negative K times RP, okay? And so we'll be able to convert, in this section, we'll learn to be able to convert decay rate and half-life and some application things as well, okay? So the constant K that we're seeing here, that is our birth rate minus our death rate when we're talking about population, right? So the population grows when the birth rate is greater than the death rate, and the population decreases when the death rate is greater than the birth rate. Hence, that's how we get that negative KP for decay. Okay, so I put it here. These are the graphs that the textbook shares with you. I put it in here just to, so you guys don't have to go dig it out of the textbook, but you can see where the growth, when you move the graph from left to right, on the first one, growth, we're going to be increasing our Y values as our X move to the right. On the second graph, you can see as our X values move from the left to the right, our Y values are decreasing, and thus we have decay. Okay? Any questions about growth versus decay? Okay. Okay, so we have a couple of more theorems. And so this one, we have theorem 10 is for our decay rate, right? And half-life. So really, it's one formula. So you don't have to memorize all 3 of these, but pick one of them to remember, because you will see a half-life question on your exam. So if you want to remember the first one, remember the first one. If you want to remember the second one, remember the second one. They're all the same, right? So let's say if I'm looking at this one and I wanted to solve for K, I divide both sides by T, and now I have this one, right? Or let's say I wanted to memorize this one, right? If I multiply both sides by capital T, I end up with TK equals ln of 2. Then I could divide both sides by K, and I end up with the third one, right? So you don't need to memorize all 3 of them. Just pick one of them, commit that to your memory, whichever one's easier for you. And I would probably say that that capital T means half-life. Half-life is really just the ln of 2 divided by your decay rate or your growth rate, or actually half-life, it's decay, because you're cutting it in half, okay? The second theorem that we have here tonight is the present value, or P naught. So we kind of talked about that earlier when we talked about population. I introduced the idea of P naught. I did introduce it a little bit before the textbook does, but I thought it fit better in our initial discussion. So basically, the present value is your initial value or the amount due at t years. Okay. So our t is in years, our k is our interest rate. And then because remember, this is like our PERT. Remember, we did that PERT, which was principal or our principal that we invested times e raised to our rate times the time to get continuous growth. It's the same idea here, except we have our r or our rate is really a negative k because of decay. Okay, so that's really all that is. So it's not really a new concept. It's just it's kind of just spelled out a little bit differently. Okay. All right. So on page 235 of your textbook is Newton's law of cooling. So we're not really going to spend a whole lot of time on that, but I've put it out here for you where you could see that the temperature T of a cooling object drops at a rate proportional to the difference in the double time minus the cooling, where C is that constant temperature of the surrounding medium. Okay. And so, but what we will spend time on is this next section about radioactive carbon decaying, essentially. Okay. So again, this section is mostly just application problems. So the first one, if we have some radioactive decay, so we're looking at carbon 14, and it has a decay rate of 0.012097% a year. So that's a really, 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 really small decay rate, right? It's not even half a percent. It's not even a tenth of a percent. It's like 100th of a percent per year. So what that's saying is, so this radioactive decay, it takes a really, really, really long time for carbon 14 to decay. So what we have here is we have this formula that the decay rate, so it gives us this here in percent. If we change that to decimal, it's this really long decimal here, right? And so we want to determine what the exponential function of the model is. And then we want to know how much, if we have 200 grams of carbon 14, at time 0, how much are we going to have in 800 years? Okay. And then we'll want to know what the rate of change is for that. And we want to know how many years it'll take to get to a half-life of the original. So how long will it take us to get to until we have only 100 grams of carbon 14 remain? Okay. So we'll walk through that in this example. So part A first is our formula, N of T is equal to our N naught times E raised to the negative KT. Okay. And so when we plug in the things we know, N naught, we know we were given that, well, so let's put N naught, it's our initial, and then E is negative, and they gave us 0.000120097 T. Okay. And so that's part A. Part B, we really just take this here and plug in our N naught. So N naught in this case, remember, was 200. I'm going to write that over here. Remember, N naught equals 200 grams. Okay. And so now we have part B was we wanted to know how many or how much will remain after 800 years. So now we're looking at N of 800 years. So that's going to be our 200 e to the negative 0.00012097 times 800. Okay. This is going to give me about 181.55186, or approximately 182 grams. So after 800 years, I've only decayed 18 grams of that 200. So that shows you just how long it takes carbon-14 to decay. Okay. So part C then asks us, what is the rate of change? So we have to take the derivative. So N prime of T is equal to, remember, that's my rate times N of T, right? And we want to evaluate that at 800. So my rate, we know, is negative 0.00012097. My N of T was that 182 grams. Okay. So when I simplify that, that is a negative 0.022. So that tells me that the rate of change of the amount of carbon-14 after 800 years will be about negative 0.022 grams per day. So every day it'll decrease by less than 0.22 grams. Okay. Questions? So the last part here is the double time, right? So, or not the double time, the half-life, right? So when we're looking at the half-life for this one, we can choose any one of the formulas. I tend to choose the capital T ln of 2 over K, because then I'm already at half-life, because capital T is half-life, right? And so this would be ln of 2 over this 0.00012097. Keep in mind that the negative doesn't go with the K. The K is part of the formula up here. So our K itself is just the positive. And so essentially this would, ln of 2 divided by this fraction, or this decimal, is 5729.91. So what that tells me, that it's going to take about 5,730 years to get to 100 grams, or the half-life. Okay. So when you see like a lot of fossil dating and stuff like that, they use this sort of technique to help them determine the age of particular fossils and things like that. Okay. Question?
Professor?
Yes.
So on C, I'm just a little bit lost. I was wondering, how do we got that formula?
This one right here?
Yeah, on C, on the part C. No.
Part,
Yeah.
Yep. So this right here was, because you haven't had the opportunity to do the homework yet, so that's why you haven't had that. But it is, we were given that right here. The derivative of something with the K times some function is K times the function. Okay, so it's theorem 9 out of section 2.4.
Okay, thank you.
But good question. And thank you for asking and not just going, I'll figure it out later. All right, any other questions? All right. So here is another application problem. This one is dealing with chemistry. So in this problem, we have a substance, we'll call it A, and it decomposes at a rate proportional to the amount of A present. So we want to write an equation that gives the amount of A left on an initial amount of A naught after T hours. And then we'll find, it found that 8 grams of A decreases to 4 grams in 3 hours. So that's telling me the half-life is 3 hours, right? Because I went from 8 to 4, which is half, in 3 hours. So how long will it take to get to 1 gram? Okay, and we'll walk through that as well. All right, so first, part A, we just need to write our equation. So our equation is really going to just be our A of T. I'm going to actually write it down here. A of T is equal to our initial, or A naught, times e to the negative kt. Okay? So in part B, so we've written our equation. Now we need to first find K. Okay? So first find K. And we can do that because the half-life, that is T, is 3 hours. Okay, that was because we went from 8 grams to 4 grams in 3 hours. So we could solve for K. So our K is equal to, so remember if we did the T equals ln of 2 over K, we can multiply both sides by K, divide both sides by capital T. And so that is the same as saying that K is equal to the ln of 2 divided by my half-life. Okay, so that is ln of 2 divided by 3, because my half-life is that. So my K is 0.23. Okay, so if I have that, then I know that A of T is equal to my initial, right? P naught equals, or we're calling this one A. A naught is equal to 8. We knew that T was equal to 3 because it gave us that in this problem. So we have 8 times e to the negative 0.23 T. So now I want to know when I have 1 left, right? So when does this here equal 1? That's what we're looking at. So 8 times e to the negative 0.23 T. So I have this exponent of e raised to some exponent. Remember back to our previous chapter, we can take the ln of both sides, right? And so that's going to, actually, before we could take the ln of both sides, I have to get rid of this 8, right? So I have 1 divided by 8 is 0.125 equals e raised to the negative 0.23 T. Now I could take the ln of both sides. And that is going to, I'm going to just come back up here. That's going to give me ln of 0.125 is equal to negative 0.23 T, because remember, we can bring that down into the front. The ln and the e cancel with each other. And this is going to leave me with the ln of 0.125 divided by negative 0.23 is equal to T. Therefore, T is approximately 9. So that tells me that it'll take approximately 9 hours for those 8 grams of substance to reduce to 1 gram. Okay? Questions? The last example I have here for you is actually, I find this one very fascinating. And honestly, I wish I had known about it when my kids were younger and I could have done something similar for them. Okay. So basically, this is talking about compounding interest and the power of compounding, and we can see the power of compounding interest with this example. So let's say that following the birth of her child, Roxanne wants to make an initial investment that will grow to $30,000 by the child's 20th birthday. Okay. And interest is compounded continuous at 6%. So what should her initial investment be to ensure that she makes a one-time deposit of some amount of money, and then in 20 years her child will have $30,000 in the bank. Okay? And so using the exponential growth function, we see that P of t is equal to our P naught times e to the KT. Okay, and so the future value, we know P at 20 is, we want it to be a value of $30,000, right? So this is the information that we were given, and now we need to solve what initial investment should we put in order to have that 30,000 at the end. Okay, so we want to have $30,000. We don't know what our initial investment is, right? But we do know that our interest rate is going to be 6%. So that has to be put into a decimal form. And then we're going to do that for 20 years. Okay. We can solve this around, really, we want to just get what is our P naught, or our initial investment. That is going to be our $30,000 divided by e to the 0.06 times 20. Actually, instead of writing all that out, let's just put to the 1.2. So when I do that, I get that it's approximately $9,035.83. So if you invested $9,036 today, in 3 years, you should have approximately $30,000 if your interest rate is if you're getting compounded continuously at a rate of 6%. Okay? Question. All right. So the last section we have here, it's only 2 slides. So I think we'll go ahead and push through with this before taking our break, and then we'll come back after break and look at the exam review. Okay. So in this section, we're going to look at using bases other than 10 or E to differentiate. So this is going to end up being where we have a to the x, or where we have ln of base a x. Okay. So if I'm taking the derivative of a raised to the x, then that's really just ln of a times a to the x. Okay. If I'm doing the derivative of log base a x, that's really just 1 over ln of x times 1 over x. That simplifies, it's really just 1 over x ln of a. Okay. And then, so that's theorems 12 and theorems 13. Remember, we have a special case. If you remember back to, if we were looking at the derivative of e to the x, right? That's going to be just e to the x ln of e. But remember, ln of e is what? 1. So that is ln of e times 1. So it's really, I mean, e to the x times 1. So it's really just e to the x. So that is a special case here that we saw in like section 2.1, I believe. Okay. So if you didn't remember that the derivative of e to the x is itself e to the x, you could apply it here to this formula for theorem 12, and you can see that it actually simplifies down to that for you. Okay. All right. Any questions so far? Okay, so this first problem we have here is we're looking at the tripling time of 9 hours with an initial population of 6. Okay, so this one we would have P of T is equal to our initial population of 6, and then our tripling time, that's 3, because we're tripling, right? And T to the, and we had 9 initial hours. So when we simplify this, right, that would be our initial equation. But so when we simplify this, this is going to be 6 times e to the ln of 3 raised to the t over 9. This further simplifies to 6 times e to the 0.1221 t. And that is, again, we're just simplifying this out here. And so if this had said, if this had said we're doing doubling time or quadruple time or whatever, then that's where this piece on the 3 would change. Okay, 3, 4, 5, however much that is. You will see this page 248 in the textbook. You'll see a couple of problems, maybe 1 or 2 in your homework that are similar to that. But you won't see that the tripling time or doubling time in this aspect on your exam. Okay. So then for number 14 and number 24, we really just want to differentiate. Okay. And so when we want to differentiate, the first one is probably one of the more simpler ones, right? We can use theorem 12 just as a refresher up here. When we're taking the derivative of a raised to the x, that's really just ln of whatever a is times a raised to the x. So in this case, we have the derivative here. So we have dy dx is equal to ln of a. A is 7, right? Here a is 7. So ln of 7 times 7 raised to the x. And that's all there is to that problem. That's just applying theorem 12. Okay? For the next problem, again, this we can apply our theorems as well. So here we don't have a log base in here. So we're still applying 8 raised to the x. That's this right here, right? This piece here is my a raised to the x. This is just that constant that we sometimes get, right? So we can just carry that 3,500 down. And now we're looking at what's in the orange box. I'm going to write that a little cleaner. What's in the orange box? That is, so that gives me that my A is equal to 0.038. So I have ln of 0.038 times 0.038 raised to the t. And we can't really simplify that anymore. We could do like some decimal approximation or something like that of the ln of 0.3038, but not necessary. Okay. Question.
Professor,
Yes.
how did you get the 0.1221 on problem 4?
Yeah. So, yep, it's just when we multiply. So if you multiply this out, what is the ln of 3 raised to the 9, right? So we're just distributing this into here. So if you end up with, right, ln of 3 times t, well, this is separate, like this divided by 9.
Okay.
Right.
Okay. Thank you.
Uh-huh. All right, so number 26, now we're getting into theorem 13, right, with the log. So now we have log base 13. So this would be dy dx is equal to 1 over ln of 13 times 1 over x. We can bring that together under one roof, and it's the ln. Actually, it's more proper to put the x first, and then ln of 13. And that's it. Applying that theorem 13. Now, not all of the problems are going to be that simple, right? But we have to give an example or two to at least see how the concept is applied. So when we step down into number 34, we'll actually be applying both of those theorems, 12 and 13, in one problem and using the product rule with it. Okay. So first we have, let's identify our problems. So we have f is equal to 7 to the x, right? And g is equal to my log base 12 of x. Okay. So my f prime is going to be ln of 7 times 7 to the x. And my g prime is going to be 1 over x ln of 12. Okay, so now applying our dy dx, or our product rule, right? F g prime plus g f prime. That's going to give me 7 raised to the x times 1 over x ln of 12 plus ln of 7 times 7 to the x. That's kind of all of, that's my, actually I put the g prime, I put the f prime first, so. Oh, I wrote this, I actually just wrote it backwards. So we had, I just did g f prime plus f g prime, which is fine with the, so this is holding in true with the, how we would do the quotient one. Because it's addition, it doesn't matter which pair you put first. And so this is that times our log base 12 of x. So, actually that is fg prime, sorry, plus, I just did f prime and then g. Okay, but it's multiplication and it doesn't change the answer. So this then is going to simplify. I would have 7 to the x over x ln of 12. There's nothing I can simplify here. I can't cancel the x in the denominator with the x in the exponent. It just doesn't work that way. Plus, but I can simplify a little bit here. We could put the 7 to the x first, then ln of 7 times the log base 12 of x. And that's the most we can simplify that problem as well. Okay, question. So this last problem that I have here for you, again, we have two problems. We have a quotient. So we have my f function is the 3x plus 2. My g function is the log base 6 of x. So f prime is just 3. And g prime is going to be 1 over x ln of 6. Okay. So we'll want to do our g f prime minus f g prime over g squared. Okay. So this gives me, we have log base 6 of x times 3 minus 3x plus 2 times 1 over x ln of 6 divided by log base 6x squared. Okay, and really the most we could do here, we can multiply this. So we bring the 3 to the front. So we have 3 log base 6 of x plus or minus. We can put 3x plus 2 in the numerator, x ln of 6 in the denominator, and then our log 6x squared. And that's really as simple as we can take that problem there. Okay. Question. All right. So it is 10 after, so let's come back at 8:20 p.m. and we will do our exam 2 review. All right, it is 8:20, so let's go ahead and continue with our exam chapter 2 review. I've gone ahead and posted out during the break. I posted this actual exam 2 slides as well as the 3 sections. So those are out there in Canvas. If anyone wants to follow along on your computer, or we'll have it here. So the exam is going to just the same as the previous ones. It is on October 23rd. It will open up at midnight on the 23rd. It'll close at 11:59 p.m. You must show your work. If there's no work, there's no credit to be received. There will be 17 questions, and you'll have 100 minutes to take that exam. And the reason there are 17 questions, you'll see a little bit later as we go through these, there are 3 questions that will count as 10 points each, as they take a little bit more time to work through. Okay. All right, so let's go ahead and get started then. So for this, for our first question here, if you had, you'll see something along the lines of this growth, the profit function. So looking at your interest formula, so knowing that if we have our growth is annually, daily, monthly, your quarterly, something like that, you're going to need to be able to do that based on this first formula, right? Here, the accumulated growth is your principal times 1 plus your rate over n, raised to the number of compounds per year times the time. Okay. If we're compounding continuous, remember that is our accumulated value is going to be our that's our principal, times e raised to the RT. In both of these formulas, know that our rate always has to be input in decimal form in order for the formula to work properly. Okay. I will not be providing the formulas on the exam, so you have to know those, right? So I put them up there in red so that you can know that that's the 2 things that you need to study and know how to apply from this problem. If you want to work other problems like this one, you can go to page 203 in your textbook and work problems 9 through 16, and that will give you a good solid understanding of how to do this problem on the exam. So for this one, we have a principal of $2,500. Our rate is 2.75%, and we want to know what our growth will be after 6 years. Okay. So if we're looking at annually, then that is my n is equal to 1 because I'm going to compound only 1 time per year. So this is A equals 2,500 times 1 plus 0.0275 over the number of compounds, which is 1, raised to the number of compounds times 6. Okay. So when I simplify that, I actually get to an accumulated value of $2,941.92. Okay, any questions on that? So I apply that same formula, right? So here I'm having my number of compounds is what changes, right? That is what changes in each of those iterations. If I'm looking at it in a monthly, then my n is equal to, I have 12 months in a year. And so I would, everywhere I have highlighted up there, the ones, I would change those values to a 12. And so my accumulated value is going to be approximately $2,947.93 after 6 years if I'm compounding monthly. Okay. If I compound daily, then my N is 365. And so that's going to give me an accumulated value in 6 years of approximately $29.48 and 46 cents. Okay, so all three of those use the exact same approach as we used in part A, but you're changing out whether you are you're changing out how you accumulate. Do you accumulate one time a year, 365 times a year, or 12 times a year? But you could also see quarterly, and remember, quarterly would be compounding 4 times a year. But if we're asked to compound continuous, then we have to use the other formula where we have our A is equal to P, which is 2,500, times E raised to the R, which is our rate is still 0.0275 times 6 years. And so that's going to give me a value of $29.48 and 48 cents. And just like when we went over the section in class, you can see here that compounding daily and compounding continuous are very close to each other. Okay. And then the last question, or the last part of this, is the doubling time, right? So how long, if my interest rate is 2.75%, how long will it take me to double my money? How long do I have to invest my money for at 2.75% in order for my money to double? So that is my double time, which is, remember, capital T over the ln of 2 divided by my rate. In this case, my rate is 0.0275. So it'll take me approximately 25.2 years to double my money. Okay. Question. Okay. So for this next type of problem, you are given this one, the instructions will say that you need to use your the principles that we learned in section 2.1 about logarithms. And so for this one, we see that ln of 1/4 is equal to ln of 1 minus ln of 4. This is the work you have to show, because this then tells me here what ln of 4 and ln of 5 are. I know that ln of 1 is 0, so I could put 0 here minus the 1.3863. So I would see that this is negative 1.3863, and this is required work. Okay, so I'll just put that you must show this. Okay, because you could have very easily put in your calculator ln parentheses 1 divided by 4 close parentheses and gotten this negative 1.3863, but that's not what you're being tested on. You're not being tested on the ability to punch numbers in a calculator. You're being tested for this one on the ability to remember those relationships where you know, adding if you have ln of, remember, I think the class we did ln of 21, and that was like 3 times 7, and we were given what ln of 3 and ln of 7 were, or something to that effect, right? And so that's really what you're being tested on here, not the ability to plug it in your calculator. Okay, questions? Okay, so for this next problem, we're looking at so for this one, we really want to just take the ln of both sides, and that's going to give me 2t is equal to the ln of 1,000. Divide both sides by 2, and I get that t equal to the ln of 1000 divided by 2. So t is approximately 3.4538. Okay, question. Okay, so for this next problem, we have ln of x plus 6 plus ln of x. Remember, everything that the ln, your ln, what's inside of it, it has to be greater than 0, not greater than or equal. Remember, if you put in your calculator ln of 0, you're going to get an error. So for this one, we know that x plus 6 has to be greater than 0, and we know that x has to be greater than 0. Okay? So minus 6 from both sides, I get that x has to be greater than negative 6. And I also have that x must be greater than 0. These are an and. Both conditions must be met. So I would suggest laying it out on a timeline. I have negative 6 and I have 0. I can highlight it has to be this way. And I also have to be greater than 0. So where are both conditions met? Both conditions are only met in this portion. So I know that my whole x must be greater than 0. So my domain in this case is going to be 0 to infinity. It has a parentheses on 0 because if we looked at this, we would have that asymptote here at 0, right? And then our graph would run something like this, okay? And so our domain is, we can get really, 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 really close to x equals 0, but we can't actually equal x equal to 0, or this portion right here will be undefined, and therefore it would make the whole problem undefined. But I could be 0.00001 because it's not 0, it's greater than 0, and I would still be fine. It would be very, very close to 0, and that's okay. It just wouldn't equal 0 itself. Okay? Question. All right, so for this next problem, we're really, we need to take the derivative of this piece right here, because the 2 is really just a constant, right? So we have my function f is this 4x, and so f prime is 4. So when I take the derivative, that is 2 times 4 e to the 4x, so that is 8 e to the 4x. You could have just skipped right to this one. I think this one is one of the ones that's probably simple enough that you could probably keep track of the steps in your head and not show work. But if you happen to write something wrong down, I have nothing to go on to give you any partial credit. So I would always encourage you to write some of your steps down so that I can see where to give partial credit. Okay? Question. Okay, so for this next one, we have two functions. So we're using the product rule. So our first one is x squared plus 3x minus 9. And our second function is e to the x. So when I take the derivative f prime, that is 2x plus 3. And g prime is e to the x. Okay, so doing my product rule is f prime is going to, or my function, the derivative of my function is going to be gf prime plus fg prime, or vice versa. You could put fg prime plus gf prime. It's either way. So g is e to the x. F prime is 2x plus 3 plus f, which is x squared plus 3x minus 9. And my g prime is e to the x. Now, I do want to point out that I have an e to the x in both terms. So instead of multiplying those out and factoring it all out, let's go ahead and just factor the e to the x out. So we have e to the x, and it leaves me with 2x plus 3 in the first term, plus x squared plus 3x minus 9 in the second term. And now all I have to do is simplify that, the inside of the parentheses, and that gives me e to the x is equal to, not equal, times x squared plus 5x minus 6. Okay, question. All right. So this next problem, we have page 210. It's similar to question 25 through 46 in the textbook. This one is number 34. I chose it because it's a little more complex than probably what you would see on the exam, but it's always good to see those implemented into practice. So the first thing I want to do is let's translate this into, instead of having that square root, this is really the same as e raised to the t, and the t is to the 1/3, right? So the cubed root of t is really just t to the 1/3. So that's all I've done, is get rid of the cubed root and changed it to an exponent. Okay. So what I want to do is, I'm going to actually, yeah, that's fine. So actually, let's make these x's, just because we're probably all in, we're all probably in the habit of writing x's. And so I don't want to add a layer of confusion. So this would just be x, okay, for the 1/3. So x, t, q, p, it doesn't matter what that letter is, so long as we apply the principles of derivatives across them the same, okay? So we're looking at this here, and so I want to do the derivative. So v prime of x is equal to e cubed root of x over 3 times e to the 2/3. And how do we get that? We get that because, let's do all the different colors. Our f function is going to be e cubed x, right? Our g function, because this is the derivative of this, right? So now we're going to do the derivative of this. So our f function is this one right here, okay? And our g function is this one right here. So our g function is 3e to the 2/3, okay? So when we take the derivative, my f prime, and the reason I'm choosing 4 different colors is when I put them down into this next, where we put our gf prime minus fg prime, I want it to be in all the different colors to kind of help you see how the complex pieces come together, okay? So our f prime then is going to be e the cubed root of x over 3x to the 2/3. And our g prime is going to be 2 over 3x to the 1/3. Okay. And so that's really just using our rules of derivatives for each of those pieces. Okay. So now going back to, I'm going to actually, yeah, green is fine. So coming back to our original equation here, when I have this this really is the same as saying 1/3, because if we're looking at this piece here, right? I can have this 1/3, bring that out to the out front, and then looking at d dx of the, so we have actually, so if this is a 1, this is the 1/3 that we can bring out, right? And then the derivative then of e cubed root of x e to the 2/3. Okay, and not e, this one is x for that first piece. Okay, and so when we look at this, we're looking at this, and how do we simplify that? So we have the 1/3. These are the pieces that we kind of pulled up over here. And so we can bring that as 1/3 our g prime, which is 3e to the 2/3 times f prime, which is e cubed root of x over 3 times x to the 2/3 minus our f prime, which is e cubed root of x times our g prime, which is 2 times 3x to the 1/3. All of that divided by our g function squared. And our g function is this 3e to the 2/3. Not 3e to the 2/3. Our g function is actually, sorry, x. So we pull that x to the 2/3. Okay, and so this is x to the 2/3 squared. So now when we simplify this, we can see here that I actually wrote the orange incorrectly right here. It's the x to the 2/3. So we have x to the 2/3 here and here. So those will actually cancel out with one another. Okay. And we also have x to the, so we can simplify now. So we have 1/3 times, and that 1/3 is out in front of all of this. Okay, and then we have times e to the cubed root of x over 3 minus 2 times e to the cubed root of x over 3x to the 1/3. So in this case, we have a common denominator we want to get a common denominator in our numerator. And so essentially, we have to multiply both pieces of that first term, right? So we already have a 3 in the denominator of both pieces, but we don't have an x to the 1/3. So we would want to do x raised to the 1/3 over x raised to the 1/3 for that first term. Okay, and so that's going to give us 1/3 times e to the 3 or the cubed root of x over, we have this common term now here in the denominator, which is 3x to the 1/3. And then we have this minus 2e to the cubed root here. Okay. And so now we have a 1/3 in the 1/3 out here, 1/3 times, we can multiply those two towards each other. And so we can get e to the cubed root minus 2e to the cubed root of x over 9 times x to the 1/3. Okay. And you could factor out one more, you could factor out the e to the cube. So that would give us e cubed root of x. And we have 1 in there minus 2 of them here, right? So, well, we don't have to factor them. We could just see that they have the common thing. So we would be left with negative 1e cubed root of x over 9e to the 1/3. So we have negative e cubed root of x over 9 to the x to the 1/3. Sorry. Okay.
Professor, where is the x2 over 3 square? Is in the orange one?
The orange one. Yeah, so initially I had written, I didn't write this as clear. I skipped a step when we do the derivative, right? So if I take the initial derivative of this first one, I'm going to do a different, let's do orange here. So we have our f is equal to x to the 1/3, and our f prime is equal to 1/3 t to the negative 2/3. If we took the derivative just of this first portion here, right? So this would give me 1/3 t to the negative 1/3 e to the t to the 1/3 if I took the derivative of that. And so essentially I probably should have rewritten this one over here as e to the t to the 1/3 as or x to the 1/3. Sorry. Let me change these to x's. But I didn't, so we have it here, but you could change it at any point, right? This could at any point become e to the x to the 1/3. It just gets like, it was just getting, it would get compounded. I thought for presenting, it looked a little cleaner like this, but to do the derivative, it's probably a little bit easier to do it when it's in that form. Does that make sense? Actually, what this problem was doing is we took this first derivative and then we took a second derivative. So if you read the, so this portion right here is for the first derivative, and the rest of it is for the second derivative. So taking the derivative of the derivative. Again, practicing, this was problem number 34. So probably if you can work like problems 25 through like 33, you can probably sufficiently get through doing the second derivative of a problem to get to the exam. Okay. So you won't have one of this complex caliber on your exam, obviously, because it takes a long time to get through. And secondly, there's a lot of room for error, and that's not what we're that's not what I'm trying to test you on, is to see if I can stump you. I want to tell you exactly what to practice. And so I would focus in on this section, but more along the lines of like 25 through problems 32 or 33, instead of the further you go in any section, the more complex the problems get. And so, yeah. Questions? All right, so this next problem is similar to page 210 in your book. And let me actually just open that to the instructions. I didn't write them on here. So problems 47 through 58, those tend to be some of the application problems. This one is problem number 50, and we're looking at depreciation. So if you're looking at purchasing a new video surveillance system and the system depreciates according to this formula, we want to determine what is the value of the equipment in 5 years, and we want to know what is the rate of change in the value of that system after 5 years. So essentially, the first part, we're just taking the 17,500 e to the negative 0.0834 and multiplying it by the 5 years. And so that's going to be a value of $11,532.87. So that means my equipment that was $17,500 when I purchased it, 5 years later is only worth $11,532. Okay. When I want to look at the how much the rate of change, I need to do the derivative, right? So the derivative is going to be that 17,500 times my negative 0.0834 times e to the negative 0.0834 t. My time I'm trying to determine is at 5 years. So I plug in the 5 years here for my time. And that's going to give me that I'm depreciating at negative $961.84 per year. So the value of at year 5, the value of my equipment depreciated $961.84. Okay, questions? Okay, so for this next one, this is page 216 in your textbook, problems 1 through 20. Here we have my f function is x to the 4, and my g function is ln of x. My f prime is 4x cubed, and my g prime is 1 over x. Y prime then, or my derivative of my function, is my f g prime plus gf prime. And so this gives me x to the 4 times g prime, which is 1 over x, plus g, which is the ln of x, times f prime, which is 4x cubed. So I could see that I have an x in the denominator and 3 in my numerator, so I can cancel one of those out. And that leaves me with x cubed plus 4x cubed ln of x. Now I could see that I have x cubed here and x cubed here. So let's factor an x cubed out of each of those terms. And I get x cubed, I'm left with 1 plus 4 ln of x. Okay, questions? So for this next problem, I need to distribute this ln to all of these, right? So I can have the ln to each of those 3 pieces. And so that is the ln of 2x to the 4 plus ln e to the 3x plus ln of x squared plus x plus 1 to the 5. Okay, so that is nothing more than just using those principles. I then need to move this exponent down into the front. So that gives me ln, actually I can, yeah, we'll do that. The ln of 2x to the 4 plus ln e3 to the x plus 5 ln x squared plus x plus 1. Okay. Now to take the derivative of those, right? So we can do the derivative of each of the piece parts. So I'm going to just put h prime here so we know now that we're doing the derivative, because this is just h. All I did was simplify h so that we can actually do the derivative. Okay. So now this gives me 8x to the 3, because we're doing this first term here. That's 8x cubed over 2x to the 4, right? Because it's my the derivative of my function over my function. Okay. Plus this would, the derivative of my function over my function. So that is going to give me just a 3 here. Plus 5 times, this is going to be 2x plus 1. That's the derivative of my function over my function, which is x squared plus x plus 1. Okay. So 2 goes into 2 one time, 2 goes into 8 4 times. I have 3 x's here, so that's going to go to 0 x's, and that would cancel to 1. And then I need to just distribute that 5 to both of those pieces. And so this would simplify here to 4 over x plus 3 plus 10x plus 5 over x squared plus x plus 1. And that's as simple as you'll be required to go on the exam. You don't have to get a common denominator or anything like that. Okay, questions? The next problem is like on page 217, similar to problem number 26. It's talking about advertising. It's an application problem. It says a model for consumers' response to advertising is given by this formula. We want to find how many units were sold when $1,000 was spent on advertising. And then we want to know what our rate of change is for our function, and then apply that at 10 if our A is equal to 10. Okay. So first of all, if 1 unit is sold, right, that is 1,000 plus 200 ln of 1, but the ln of 1 is 0, right? And the reason we chose 1 unit is because we really wanted to choose 1 to make that ln go to 0, so that we could say that selling 1 unit gives me, I spend, how many units are sold when $1,000 is spent? 1. Okay. So now let's take the derivative, or find the rate of change of that formula. Well, the derivative of $1,000 is 0, right? Because that's constant. So we really only have to look at what is n prime of the ln of, or 200 ln of A. And so that's just 200 divided by A, right? 'Cause that's my, excuse me, that is the 200 divided by A, because the 200 is just a constant. And ln of A, it's like saying ln of X, which is 1 over X. So in this case, it would just be 1 over A. So now when I evaluate that then for 10 units, then I get 200 divided by 10. And so that is a value of 20. Okay, questions? So this next one is like the problem that we covered today. It'll be very simple. It'll be like theorem 8 in your textbook. And so we have d of r dt is equal to our k times r, which is r is equal to the c times e to the kt. Therefore, we just take that information and we transpose it into saying that then that our r of t is equal to ce kt. So again, this is just very similar to the problems we worked today in class. The one we looked at today, I forget what the constant was. I think one of them was a -3. And one of them, I don't remember what the other one was. So, but again, just review those couple of problems, first 6 problems there in that section, and you'll see something similar to that on the exam. Okay, so here's the first problem where it's worth two problems. Okay, and so this is looking at a problem where page 226. This is out of section 2.4. And this one is application. And so we're looking at compounding interest. And so if an amount P naught is deposited into a savings account and interest is compounded continuously at 4.3%, we're given this formula here, dp over dt is 0.43p. We want to write the formula in terms of P naught and our K there. And so this would give me, again, we're at theorem 8. This is like theorem 8. And this is P of T is equal to our P naught e to the RT. So P naught, we don't know what that value is right now. So that would just still stay there. And then we'd have raised to the 0.043 T, because we do know what our K value is, right? So this here is my K. So suppose we deposit $20,000. What is our balance after 1 year? What is our balance after 2 years? So it's telling us to suppose we deposit 2,000. So that is my P naught now, my initial value. So after 1 year, that's going to be $20,000 times E raised to the 0.043 times 1, because it's after 1 year. And so I will have approximately $20,878.76. If I want to know how much I have after 2 years, I'm still with my initial $20,000 investment times E to the 0.043. But now we're at times 2 years because our time is T. Now I'm going to have $21,796.13. Okay. And then similarly, it's asking us to do the rate of change. Remember, the rate of change is just P prime of 1 is equal to my P1 times my interest rate. Okay. So that is 20,878.76 times 0.043. So my rate of change is a growth of $897.79 per year after the year 1. right? But if I do the growth change after 2 years, then that's P of 2 times K, right? And so that gives me my 21,796.13 times my growth rate of 4.3%. So that is $937.23 growth per year. Okay. Questions? So the next problem, again, 2 parts or 2 points, counts twice. It is about carbon dating. I will give you this value of carbon dating on the exam. You do not have to memorize it. I will give you that value on the exam. Okay. So this problem is asking us, how old is a piece of wood that has lost 90% of its carbon-14? Okay. If it's lost 90%, that means 10% remains, right? So if I have an initial value, right, my initial value, but I'm only 10% of my initial value, right? My P naught is equal to, before I do that, so we have our P naught is equal to P naught E raised to the negative 0.1230 zeros and then 12097 T. Okay. But I have 10% of that, right? And I also have a P naught on both sides. So essentially, I have 0.1 is equal to E raised to the negative 0.00012097 T. So I can take the ln of both sides, right? When I take the ln of each side, I get the ln of 0.1 divided, well, is equal to negative 0.00012097 T. Divide both sides by the negative 0.00012097. Okay, and I get that T is equal to 19,035 roughly, or 30, it's like 34.35. So we could say that that piece of wood is about 19,034 years old when it has 10% of its carbon remain. Okay, questions? All right, one more problem of being worth two problems on the exam. So for this problem, another application problem, this one comes out of section 5. This one is number 50. And it wants to look at the decline in beef consumption. So the annual consumption of beef per person was 64.4 pounds in 2000 and 61.2 pounds in 2008. Assuming that the beef consumption T years after the year 2000 is decreasing according to exponential decay model, we want to find the value of K and write the equation. Then we want to estimate the consumption in 2015. And also we want to tell when we think the consumption rate will be at 20 pounds per person. Okay. So I've given you the formula here, which is B of T is equal to our initial beef consumption, right? So this could be the same as population of P naught E to the negative KT of T, right? It doesn't matter. I just chose B because it is beef consumption. Okay. And T is the number of years since 2000. Okay. So how do we put this? So basically, we would say that 2008, that gives me T equals 2008 minus 2000. So T is equal to 8. Okay. So my consumption in 2008, right? So we're looking at 2008. So 61.2 is my consumption, is equal to 64.6 pounds E to the negative K times 8, because we're 8 years removed, right? I need to divide both sides by 64.6 because ultimately we're trying to be able to get E to whatever exponent by itself, so we could take the ln of both sides. So this is going to be 61.2 divided by 64.6 is equal to E to the negative K times 8. So now I can take the ln of both sides. Okay, when I take ln of both sides, I end up with a ln of 61.2 over 64.6 is equal to negative 8K. Divide both sides by negative 8, and I get that K is equal to 0.0068, or K is equal to 0.68% per year. Okay. So when I have that, that then gives me that my B of T function is the 64.6. That's my B naught times E to the negative, my decay rate, my K is 0.0068 times T. Okay. And so when I want to know what my estimated consumption is in 2015, that's going to be my T, which is 2000 minus, or not, 2015 minus 2000, means that my T is equal to 5. I mean, not 5, 15. Okay. So B evaluated at 15 is this 64.6 E to the negative 0.0068 times 15. And that equals 58.3 pounds per person. Okay, so in 2015, the beef consumption is down. In 2000, it was 64.8, 2008, it was 61.2. So you can see we're steadily declining. Till the year 2015, we're now at a consumption rate of about 58 pounds per person. The last part of this one wanted to know what would the consumption be, what year will the average person be consuming 20 pounds? So we want our B of T, the solution, to be 20 pounds per person. So if that's the case, we're saying 20 pounds is equal to our 64.6 formula, E to the negative 0.0068 T. Okay. We divide both sides by the 64.6 because we have to get E by itself before we could take the ln of those. So that's going to be 20 over 64.6 is equal to E to the negative 0.0068 T. So we can now take the ln of both sides. And that gives me that T is equal to 172.4. So you have to then go back. Remember, T0 is 2000. So 2000 plus 172.4 is the year 2172 is when they project that the average person will be consuming only 20 pounds of beef per year. Okay. Questions? Okay, the next problem, we're back to, this one doesn't really require any work. It's like theorem number 12 that we covered tonight. So the 24 stays, and then we're really just taking the derivative of 9x, and that is, or 9 to the x, so that would just be ln of 9 times 9 to the x. So there's no work required for this one. Okay. Questions? All right, so the last problem that we have here, this is applying that theorem number 13 that we did tonight. So first we have our f function is 2x minus x cubed, right? That's what's in here. That's my f function. My f prime then would be 2 minus 3x squared. Okay, so my derivative is going to be 8, that 8 stays, times my f prime over f, right? So this is really just 8 f prime over f, which is 8 times my f prime, which is 2 minus 3x squared, over f, which is, well, so we have to do, oh, the ln one, sorry, is going to be, yeah, sorry. So it is 8 over the ln of 3 times 1 over my f, which is 2x minus x cubed. So I split them out here just because they became compounded, but I could have just combined those under one roof as well, right? Because remember, theorem 13 from earlier this evening was where we would have our the derivative of the log, which is d dx of log a x is equal to 1 over ln of a times 1 over x, which is 1 over x ln of a. So really that's, you could write it in this form or the expanded form. So, but what we want to do here is we want to combine them under one roof. I'm going to just move this off to the side. We'll just move it here. We'll make it another color so it doesn't get confused. Okay. So we can distribute the 8 to this, and we can distribute the denominators. And so this is going to end up with 16 minus 24x squared over 2x minus x cubed times ln of 3. Okay. Question. All right, so that is all of the material that I have for you. That is all the material that you should expect to see on exam 2. Again, exam 2 is not until the 23rd of October. So that means you have 3 weeks to work with this material, prepare with this material, so that you are prepared, because there are some things that are a little wonky when you're dealing with exponents and logs and things like that. So we'll have plenty of time between now and then where you can ask questions and things like that. So, but don't forget, next class period, or next Monday, we don't actually have class. It's a holiday. The college is closed. It's not a holiday. The school is calling it fall break. It does happen to fall on a federal holiday, but it's just fall break for school purposes, not a day off because of the holiday. Okay? All right. Do you guys have any questions for me? All right. No questions. So you are free to go. And then I will see you all here 2 weeks from tonight to do our chapter, to begin our chapter 3 lecture.
Thank you, Professor. Have a good night.
You're welcome. Thank you. Have a good night.